Let's do a quick recap of the setting which we have discussed for PRNN. As we have discussed earlier, uh, this is actually uh, the course which is based on the PRNN course, which is Pattern Recognition Network course taught at IISc Bangalore by Professor Pratush. So notes and course structure will be mainly following the official course taught in IISc. Yeah, and we'll be taking the notes and all, which we'll be borrowing from there, just to credit him. Yeah. So let's take a look at the basic setting which we've discussed. As we have seen in the previous class, in fact, this is the first class. The previous class didn't get recorded. Anyways, this is in this class we'll be looking at what is a machine learning problem. How can we set it up in using both approaches, which is a deterministic approach and a probabilistic approach. Is there any way I can use any kind of a right? I don't know how to point on this. Fine. Yeah. So what we have right now is something which we have called as data. We are given with what we call as data. Let me just parallelly mark the points which we're covering so that we don't lose track, right? So we have something which is known as data, and data is normally divided into something which is known as a feature space and label space. We have a data space. It's divided into both these spaces. Need not be always. We'll see that later as well. Currently, let's understand the setting. Xi is a particular data point which is in the data feature space, and its corresponding label is something which is in the label space. So what we have note here is that data can be RD, it can be a D-dimensional. As an example, you've seen an image which is 2 cross 2. In that case, the data is 4-dimensional, R raised to 4. And label can be in R raised to K space. It can be continuous or discrete, and even data can also, the feature space can be also continuous and discrete. Both are the possibilities. An example of label space which you can look at is a cat and a dog, which is a binary space. Which is a binary label. What is the setting? It's not even, it's of course one dimensional. And it's just two discrete values, a set of two values. Okay. Yeah. Another example is, let's say we have a regression setting. This kind of a problem is basically known as a classification problem, and we can also look at something known as a regression setting of a machine learning problem. For example, we have a bunch of documents, and each document has d dimensions in terms of the words which we have. For example, let's say the simplest ways of modeling data is something which is known as bag of words. So for example, the data is about, let's say mathematical paper is difficult to model. Let's say it's an English paper, or let's say it's a biology paper, and it's about plants, right? Then we have different sorts of plants in it, which we classify. Just like each value of word can take different values, and it's like a d-dimensional. If there are different set of words, it's a d-dimensional data in every document. So every document is a d-dimensional data in that way. So how does the regression setting work? Suppose it's an exam and it's like a one-word answer, and we have to basically evaluate the label is as a number, a mark of that corresponding paper. Then it's like a regression setting. Okay. Now then we discuss on something which is known as a probabilistic viewpoint of machine learning. Data is, so every data point which we have formulated as an ordered pair of xi comma yi is treated as points which are sampled IID from an underlying distribution P of xy, joint distribution Pxy. I note that it's a distribution and not a density function. It's a distribution function because the distribution function always exists and density function need not exist always. Fermi-Stoma in stochastic model course you should be able to know this. So the basic setting here is okay, so we understood what we have in hand right now, and now we have to define what is the problem of learning. So what we have here is something which is called as a data, a sampled IID from Px or Pxy. So here is a difference in the setting. I mean, there's no major mathematical difference, but as far as the application of such a problem is concerned, or there's a slight difference. There's something which is known as unsupervised setting and the supervised machine learning setting. In unsupervised setting, we are not separating the spaces of data and labels, I mean features and labels. So they are both treated as together. And they're both treated together, it's known as unsupervised setting. In supervised setting, we're just separating it out. X and Y are separated out as two different spaces, but mathematically it doesn't make much of a difference. I mean, no difference at all. Because here also we have noticed that x is actually a vector valued random variable, and in fact when we take a joint distribution of xy, its y is another vector valued random variable. So if you merge y in this particular x, y is actually included. We're not separating out those spaces. That's all the difference, right? Okay, in this setting what we do, so we have to this is a sample, and yeah, so we were looking at it, right? So yeah, and how does the probabilistic setting go? So when we're given these data points, we have to estimate Px or estimate the joint distribution Pxy. That is the basic understanding. How do we estimate is basically what comprises of the course, the probabilistic sense. Now we'll look at something called as a deterministic viewpoint of the machine learning problem. So here we have a data point and a corresponding label. So we know that for a particular data point there is a corresponding label, and we are given with a number of data points and its corresponding labels, right, which can be seen as an ordered pair of x and y, which is known to us. We have a number of data points, and something which we have noticed here is data point can be in RD dimension, in D dimension, so it is like RD, and label space in RK. So is there a function which takes all these data points and maps it to its corresponding labels? That is the basic question. But the difficulty which we face here is that how many functions are possible in this case? Because since these data space as well as the label space is having infinite cardinality, infinite number of functions we can learn here. So it's like infinite functions. Infinite functions are possible. So how do we find the function which is learning this? So whenever we have a lot of functions, we have to restrict our set of functions which we can consider. So for that, which we define something known as a loss function. Loss function is a cost which helps us to restrict the function, like to find an optimal function. So we basically cast this as an optimization problem in which what we do is we find a function. There's a loss function which is a function which has a domain space as h of x cross y and takes to R plus. I mean, it gives a corresponding cost to every data label set. It has a particular cost. So what do we need to do? We have to basically minimize this loss. That is how. And the hypothesis which minimizes this loss is something which we want to find, right? And by the way, why this is R plus is pretty obvious, because negative loss doesn't make any sense. And one more thing which we have a slight modification here is so we have to note that LS loss function is actually a pointwise function. It acts on every point. Okay, point of the distribution. No, distribution is not the right word here. Point of the data. Yeah, because we are in the deterministic setting, and again going back to the word distribution doesn't make much sense. So we have to take something known as an average loss, which is the basic idea. When we have n number of set points or n number of data points, the very obvious way of extending it to all the points is take the average of the loss function. So for that purpose, we are actually finding the expectation of the loss function, right? So basically and this expectation value function is known as the risk function. So our basic setting of this deterministic problem of machine learning, it boils down to what we call as minimizing the optimization problem of minimizing the risk and finding the hypothesis function corresponding to it. Okay, so to summarize what we have seen so far, we have seen that there are two ways in which we can approach ML, which is actually kind of complementary. It's not like one way is completely completely goes in a different direction as the other. We have to parallelly look at both views and sometimes use some results back and forth and learn this. Okay, and we have a data point. Okay, what is the probabilistic viewpoint? We have a data point which can be label separated, or the labels can be put together. If the labels are put together, it's known as unsupervised learning. The labels and data features are put separately, it's known as supervised learning. In both these cases, we have to estimate px or pxy, joint distribution. Deterministic setting, we have a hypothesis function which takes x to y. Since it's having an infinite cardinality, we have to cast it as an optimization problem. Now, what is the optimization problem? Since we have to we basically have a loss function, but loss function is pointwise, so in order to include all for generalizing it over the entire data points, we'll find the estimation expectation of the loss function, and we'll find the hypothesis function which minimizes the expectation of the loss function, which is known as the risk function. So we have to find a hypothesis which basically minimizes the risk function. This is the deterministic approach. So going further, we'll be looking at how to estimate this pxy. Is it actually possible to estimate pxy, or which are at least the best possible estimates of pxy, and how to find the hypothesis which minimizes the risk. All these things we'll be covering in the following lectures.